Thank you. So we have a great panel here of drilling experts, all different steps of deployment and disciplines, and I'm going to let them do an overview of their method of choice and when it's ideal. Beyond that, we have about 20 minutes of questions amongst us that we have developed, and that's going to leave us 20 minutes of questions for you all. The one thing I'm going to ask is be brief and brilliant with your questions. This is not a monologue or a soliloquy, and I will cut you off. So let's get our point across so we can get back and we can get as many questions as possible. So I put 2 slides in here before we started. And as we think of what our drilling contractors, our bid process, and what we need from equipment availability to hole specifications to cleanup and disposal, and we're hearing a lot about cleanup and disposal and waste removal, right? This slide right here came from multiple GCs on projects all over the country on what's impacting projects, what's happening with change orders. And we think of why we get to increase drilling cost. And I just want you to take a look from drilling-related methods to other construction operations, man-made subsurface obstructions, contaminants, weather. So we all need to think about that as we're choosing our drilling disciplines. With that, I'm going to start right here with Kim with Rototec, and I'll let him introduce himself, and we'll get rolling.
Thank you, Brock. So my name is Kim Ojanne, and as you can hear, I'm from Sweden. I moved here to US last year in July, and really enjoy it. So thank you for the opportunity doing that. I'm not used to present for this many people, but it's going to be nice doing that. And I see also a lot of drilling experts out there, so hopefully we can have an interesting discussion. So what are Rototec doing? We are doing the down the hole hammer drilling, and what's the advantages of doing the DTH drilling, and what are the disadvantages? So DTH is a very efficient method for doing drilling in hard rock. So when we decided to come to US, we decided to come to the Northeast because that's a quite good area for us to drill in. There are other areas that doesn't fit us very good, and there is definitely better drilling technologies for those areas. And of course, Northeast is a quite big area, so there is also local variations also here. So when we are looking into a project, we need to look into geological conditions, water well logs. There's a lot of information that we need to gather to make a good assumption of can we do this project in a good way for our client. DTH is a cost-effective way of doing drilling in hard rock. Versatility can be used in various types of rock formations, and the depth, which is quite interesting. I mean, the New York changed the regulations from 500 feet. DTH is a good method going deeper. It doesn't mean that we should go deeper on every project. We should do a test hole and find out what is a good depth for this project if we design in 800 feet boreholes, but this project is, we have a big seam and cracks, we should not go deeper than 500. So let's find out doing test wells. And if you can go 800, that might be very good economics for that project. Disadvantages of DTH, high energy consumption for drilling. When we go deeper and deeper, we use a lot of money, the energy, to not actually drilling, but we are wasting the energy. So that's a disadvantage. And we can develop that a little bit. Less effective in very soft rocks. Not too interested going to Long Island, for example. That's not a market for us. So yes, that's a fact. Yeah. CapEx intensive compared to some other drilling methods. I mean, drill rigs costs. it's not DTH only that costs money, but this is a CapEx intensive business. How do I change slide? Yeah, so this is how it looks like. This is a geothermal well drilling project for a residential. We did it in February in Ithaca, New York. Actually, it was better weather in February than March. So, as you can, our technologies, we have truck trailer, and we have the drilling rig and the compressor. So easy mobilization. We go to one site, and the next day we hope to go to the next site. So logistics is a big part of drilling. And then when we enter the site, we have the drilling rig, easy to move around, and this is actually a quite small spot. So we keep it as small as possible to actually be able to deliver geothermal wells for residentials in urban areas. Capacity, we're running 507 PSI, 1228 CFM, so we are capable of doing a lot with it's small, but it's powerful. You cannot see it, but we have the dumpsters and the water treatment, so we can collect the drill cuttings, and that's a big difference for a client to decide to go into geothermal. They might be scared. How will this look like when we're done with the drilling?
You have 1 minute left, Jim.
Okay. And the little bit more futuristic part, so we are doing today IoT and AI. This might sound crazy, but drillers they are really good, and they can listen what happened in the borehole. But will the future generation be able to do that? So we put sensors on the drilling, and we take that sound, because when we're hitting the rock with the drill bit, we might hit the same spot all the time. And if we can get that rotation and so we hit different parts of the rock, then we will be more efficient in the drilling, and this is how we can train the drillers also. It doesn't mean that with IoT and AI you will be a driller, but it's a good, helpful part. So this we're developing a lot, and yeah, this is one future part I see in this industry. Of course, this is still hard work, and we need to find the right drillers, but we will help them whatever we can do with the training. Thank you.
And if there's a rocket scientist in the industry, it's Dmitry right here. So everybody pay attention.
Not really rocket science. I'm trying to be more simple. But basically my background, I come from oil and gas. I spent 13 years in Middle East drilling for oil and gas, deepest and longest wells on my record, up to 45,000 foot. So now we're just downsizing a bit, and we're trying to carry the technology and lesson learned and practices which we learn in the big and basically CapEx intensive drilling operations to much cheaper operations, but the main target to make it cheaper and more efficient. So in our case, when we talk about Celsius Energy and what we're different and where is our playground and what's basically the best application for us, we can basically play on the big fields, or we can play on the very small fields, because our unique proposal is basically a star topology approach when we collocate our wells. And the reason why we can collocate our wells, we basically have a technology to provide directional drilling, so we can basically collocate the wells and spread out them in the shape of the sun from the single point. As a result, your shape of your field, borehole field, is changing, correct? So now you have an area, could you imagine, 7 by 20 feet only, where we can place up to 21 bore. Like in this example, we've done simplistic approach. We basically model 21 bore star topology, and the same amount of energy we can produce from 24 wells basically as a classic distribution at 20-foot spacing. So what is give us, so we can see that when we go inclined, first of all, we managed to save 13% on the drill length. So we basically need to provide less wells to provide the same amount of energy. We talk roughly about 1700 MBTU system. But what is really important, and this is what many people don't talk, when we talk about geothermal project, it's not about drilling, it's about total construction cost. And the total construction cost, there is almost 40 to 50% of the construction involved besides the drilling, where you need to put the piping, fusing, you need to groundwork, you need to remove this ground. So, and when we take a look at these numbers, this is where there's a huge difference coming. So we're saving almost 78% of the piping because our wells collocated. So we're installing the bore for manifold just in the middle of the, basically our star, and then connecting the pipes directly there. So we don't need to run the long piping and etc. And the best part in terms of surface impact, I mean, could you imagine you're just using 7 by 20 square. This is exactly what we need to place the same amount of wells, which you will need to, on the traditional approach, you will need 150 by 70 foot field. So this is extremely big savings in terms of construction cost. And then you have really good savings on energy efficiency side, because at the surface, the wells collocated closer. We probably talk about 1 to 1.5 feet at surface from the bore to bore. But when we spread them out as a sun, we talk about roughly 60 to 80 foot between the bores as they spread out. So you have almost 4 times more energy access compared to the traditional approach. This helps us to dissipate the energy. And what is good, this system behave really, really well in unbalanced loads, which we see quite often. And especially the more we see energy improved, energy efficiency of the buildings improved, the more uneven load we see on the buildings. So this system is able to absorb this uneven load quite easily, and we don't see any temperature drift on them. So they behave extremely well. So how do we deliver, correct? So to be able to deliver such a type of systems, there is a few critical points to have. One of them, we're using the double head rigs, which are able to incline the mast. So we didn't find the track-mounted rig with inclined mast, so we go at traditional like construction site equipment. There is quite a few providers, like Clem, GTD, NY-GEO, Casa Grande. So what we're looking for increased pullback capacity, because as soon as we get the angle, we get a drag and gravity act against us. So we need to have a lot of pullback capacity to be able to retrieve the string. And the second part of the equation is basically assembly, to be able to control the direction where we're drilling. We don't use any smart motors like in oil and gas. So the way we built our control of trajectory through the proper stabilization and adjustment of the assembly itself. So this is where the most of the investment coming. There is a challenge, I would agree, because what we meet in the current industry, this requires extremely high tolerances on equipment in terms of diameters. So every piece of equipment you put in the hole, you need to measure OD, ID, and you need to know exact diameter of the equipment going in the hole. Because just tolerant, I mean, we had challenges, for example, on the last project, we get all our equipment from oil and gas providers, and the tolerances was 0.01 inch on the all manufactured pieces. But we get the bits from the oil water well industry. And when we drilled and when we measure, we observed that the assembly doesn't behave as we expect. So when we measure the bit was out of tolerance. The bit was 0.1 inch smaller than we ordered. So we was ordering 6.5 inch and we get 6.4. So we come. Okay, thank you. So this is kind of challenges we meet, and something to definitely can be addressed, and this is just a learning curve. So besides the custom bits, we're looking for design software, so to be able to plot the wells and to design the assembly. And some extra pieces, as Kim already mentioned, it's about cuttings management systems. This we see where it can be quite dramatic, especially on the big projects. We're looking for the high pressure pumps, because the way in the inclined wells, we do the sacrificial trimming. As a result, to be able to pump the grout at 600-800 foot wells, you need to have much higher pressure and adjusted trimming design. Custom reeling systems, to be able to run the system, not pushing them, but you're basically using completely different approach. This way you make sure that your loops stay intact and at the depth. We're using fiber acquisition for at least the test bores. It helps us a lot in terms of characterizing the grout job quality and potential of the ground, and surveying capacity. So we basically survey all the bores we deliver to make sure we know where the bores do reduce the collision and to spec the system as built. I think that's it. Not much from the rocket.
Thank you. We can definitely grab questions. We have McGladdery with Derex, who is an Imagineer.
Thanks. Brock said this was an Alcoholics Anonymous meeting. My name's Derek. I'm kind of the head engineer, or not engineer, imagineer of the Derex dual rotary. Dual rotary, I've had drilled all my life, and I've never found a system so simple to get to the rock. Basically, what we're doing, we're taking the top drive, the lower drive, we're turning the top drive, turns the center rods, the lower drive turns the casing. Being able to drill through boulders, keeping our hole straight and on target is the easiest way of, I find it the easiest way of drilling. We can pull into the casing, and we'll do this in sands, heaving stuff, dry gravel. When I'm losing circulation, I like to come inside the casing to keep my circulation. But the easiest and fastest way is if I can get outside of the casing a little bit and everything continues on down the hole. The best part about doing a dual rotary system is maintaining a straight hole. I can take a 28 horsepower drill and go 1,800 feet with it in rock. If I'm in overburdens, I need a little bit more power and I'll need to maintain a straight hole. When you're drilling angles, also, the biggest concern for us is always getting the casing in, and with the dual rotary, I find it's the easiest way of doing it. That's about it. I was quick. See? That's just dual rotary.
We'll have plenty of questions. And last, we have Robert Meyer with Thermex Geothermal. He's going to talk sonic mud.
Thank you, Brock. So really quick, I'm going to go through sonic first and then go through, it was planned for rotary, but I'm just going to do a general description of direct rotary methods, which includes mud and air and others. What is sonic drilling? Sonic drilling uses high frequency vibration combined with a drilling fluid medium to cut through unconsolidated and consolidated lithologies. Traditionally used as a system of core barrels and casing, so where you are using a core barrel to advance ahead and then overriding a casing through that core material behind it. There are applications and new technologies that various manufacturers are coming up with to either eliminate the need of casing or reduce the need of casing to improve the overall efficiency of sonic drilling. But the primary advantage is that in very unstable formations, formations with a lot of groundwater, high groundwater transmissivity, conditions where you'd have collapsing boreholes, caving boreholes with other drilling methods. Sonic, like dual rotary, uses a casing system to help isolate those unstable zones. During drilling, the drilling equipment generally takes up a smaller footprint than other traditional drilling methods. However, moving between more locations can be more difficult than other methods, depending on how the equipment's set up and what kind of footprint you're having to work in. Overall, sonic is a great drilling method with highest productivity in unconsolidated, high groundwater bearing containing soils. So this was, like I said, traditional rotary. There's a diagram to the right, which is a very simple look at a traditional mud rotary drilling system, where you have your drill stem and direct rotary, as it's called. You're drilling mud or air or foam or whatever flows down the inside of the drill pipe, comes up that outside of the drill pipe between the borehole annulus. It uses rotation and downforce, generally provided by the drill string itself, to advance. It's applicable in both unconsolidated and consolidated lithologies. Your choice of medium will likely depend on whether it's consolidated or unconsolidated. It's most effective, mud rotary is most effective in unconsolidated lithologies. Mud rotary does require some sort of fluid and solid separation system at some point at the surface. And so getting back to one of the comments about waste generation and disposal that Brock made earlier, that's an important consideration. As far as the actual bits and bottom hole assembly that are used, you have a million options that can be configured for the specific site. And one of the things that we'll get into later on in this discussion is right sizing the drilling for the specific site location based on the conditions that you're drilling in, and not copying and pasting a spec and it worked over here so it's going to work over there. Every site is different. And every bit that you use in stabilizer setup and how you construct your bottom hole assembly is always different. As far as efficiency goes, rotary drilling, direct rotary drilling can be extremely efficient when everything's set up well, the lithology is understood, and it's well planned. I think that's it. Is there anything else? Hey! It's not endless back there. I had too much coffee and I'm walking around too much, so sorry about that. I think that's, I'm done.
Excellent.
Cut that part from the video.
So we'll get started with some questions. So we've talked about our methods and whatnot, but from a site constraint, why choose a specific drilling method? I'll let you guys open it up. Brief, brilliant. Go ahead.
I mean, so one of the things that Kim brought up was identifying with down the hole hammer the conditions that are required to maximize efficiency. And every drilling method has different conditions in which it is most effective and most efficient. And one of the things that across the board is being spoken about is reducing cost for these installations and maximizing the budgets that are available. And so it all starts with understanding, doing a test boring, and understanding the lithology available at the site that you're drilling at, and then deriving the drilling methodology selection. There's not one that's better or worse or the best or the worst for making a hole, but rather what is the best for that particular site.
Anything to add, or do we want to move on?
If we talk about the site selection, probably, yeah, I would agree. So the first we go for the pilot hole, test hole. So you basically define your geology, and something beyond geology. For example, our latest pilot hole, we basically we knew that we will encounter water. We're already for 150 gallons a minute, and we basically fully set up. But somewhere at around, for example, 600 foot, we hit 1,000 gallons a minute. So this was the second fracture. It's something we learned. So we knew how we adapt. We've been lucky. We had a fiber optic line in the completion. So when we start to do our grouting job, we managed to basically see in real time as we grout, we can see where the grout is setting up and where we're losing the grout. So we basically managed to seal the bottom fracture, and then we managed to basically pump it and seal the second fracture. What was cool about this, because the bottom fracture was a high salinity brines, and the second fracture was a fresh water. So this was a kind of critical operation. We managed to isolate them both with the concrete on the bottom and the bentonite concrete on the top. And what it's showing you here, it's not just show off, it's basically in the next operation, like we're planning another 40 wells. Now I will cut my wells at 540 foot instead of 580 where we hit the first fracture. And this will help me to save a significant amount on the project. And now we will have a defined grout program as well. I know where is my fracture in the grout, and I know till what depth I need to pump the proper bentonite mix, then where I need to pump the concrete to seal the fracture, and where I need to pump the rest of the bentonite. And this will help you to save a lot on your grout and on the timing of the grout jobs as well. So just one of the examples how the pilot bores can help you and save on the operation.
We'll move on. From a hole specification standpoint, you know, choosing the right drilling method. We just heard Derek say that he could use 28 horsepower and drill to 1,800 feet, you know, and that's fly-in rigs with wireline coring. But, you know, let's talk about that rig size, that compressor, you know, what is required for an ideal hole specification to be successful. Yeah, go ahead.
Oh, yeah.
Well, it all comes down to it. I mean, Brock and I have both worked in the coring industry, where we take a very small rig and we fly it in under a helicopter and set it up on a 10-foot by 10-foot pad, and that's what we have to deal with. That's kind of part my world too. So what we're trying to do is reduce a footprint. I've probably got one of the smallest DR drills with a compressor on board that is mounted on a truck. I haven't touched into the tracks yet, but we're trying to reduce a footprint. Brock and I have both been around the world in our other life, but I learned that in South Africa they have a rig that could fit in these two tables, and they're drilling 10,000 feet with it. So it's not the size of the drill necessarily, but what you put into it. It's a solution. It's not just a drill, or it's not just this, or it's not just that. It's a solution based.
And so if we expand further on that, ideal borehole specifications for a bore field, horsepower, let's think about time and efficiency, right? And that's where we end up. So
Air is about the least efficient thing that we can work with.
well, we can open it up to Dmitry, Kim, and Robert.
I think when you talk about speccing the rig and speccing the size of the hole, you need to start from beginning. I mean, what you want to accomplish, correct? So you come to engineer and he tell you you need to get from this field, you need to get this amount of energy. Then this is how many bores you need. This is what depth and this is what completion is. It will be 600 foot, we go 1.25. It will be 800 foot, we go 1.5. We go quad loops. So the design of the completion will define the size of the hole, and then you start to play it back, correct? So now, for example, I have 800 foot bores, quad loops. Okay, I need to go 6.5 inch at least to be able to clear up and successfully run the completion. Or, for example, I have another project like we just completed now, 1.25 single loop, 600 foot. Okay, so then the hole size will be somewhere around 4.5, 5 inch to be efficient. And because the jump from 5 inch to 6.5, you're losing roughly 50% in drilling efficiency, and you're increasing your materials like by another 50%, almost magnitude of 2. So this is increased cost. So it depends on what project design you adapt for it. But for example, in our approach, we're trying to look for the rig which basically can accomplish both tasks, the simple small wells and the bigger wells on the commercial projects. This is the reason why when we're speccing our rigs, we're looking for double head, we're looking for the pullback capacity, but because we go incline, you're fighting the gravity, and this is where you don't want to lose your assembly down there. This is the reason why for us pullback is critical. On the vertical, it's probably maybe less critical, but for us, this is kind of one of the most critical pieces. And then you go to the compressors, and it's something we learned with Kim, for example, and I really appreciate. We're going for the high pressure compressors because this is just mechanics of the air hammers, the way they work. The higher you apply pressure, the faster you drill, and drilling is a money. So this is another piece where we optimize as well.
Yeah, that's another little great point. It seems weird and it's counterintuitive to a lot of people that you put a bigger drill pipe to get the uphole velocity increased, but when you run into groundwater, it's actually in reverse. So you run a smaller drill pipe and a larger hole so that you can dump the groundwater and the air out so that your hammer keeps going deeper.
That's a good point. Robert?
I think there's one other condition. One of the things that Derek brought up was there's a rig that can fit up here that can drill to 10,000 feet. And really it brings to mind a discussion of going back to Dmitry's point, what are the goals? And not just of the performance of the geothermal field, but what are the goals of the project as a whole? Is waste a significant issue? Is waste disposal a significant issue? Are we encountering briny water? Are we encountering salt water? Are we encountering other environmental contaminants in any amount of waste greater than what the soils that come out of the hole is just not going to work from a budgetary perspective? That directs your drilling methodology just as much as the lithology. And so it's very critical to open the door to the drillers that are involved in the project to say, here's what we need to have when we're done, but here's all the other constraints that we need to work within, and allow the drillers to bring their ideas to the table to help drive the actual selection of how the project gets done, because yeah, maybe it takes 3 months longer, but if it saves $250,000 in the process because you weren't generating as much waste, that's just as valuable.
Very interesting. A few comments. When we look at the compressor, so we use the 507 PSI, but when we go and do residential works like 400 feet, it can be, that compressor is oversized. So we could have a setup where we have smaller compressors and bigger compressors. And then what kind of geological conditions are we working in, and what are we trying to achieve for the customer? And of course there is economic perspectives, and then there's like the geological is always limiting what we can do in a safe way. I mean, we're not going to drill through drag gas and all these problematic areas. But just for an example, if we go into urban areas in the Nordics, we run up to 2,400 feet, and then we do shallower wells, which is like 12,000 feet, and then we have a few deep ones. So we can take more energy from the deep ones and redistribute to the whole borehole field. I mean, we're not there yet, but you will see what I'm trying to say. You will see different kind of solutions. It's not like the deep wells are the only solution. You have, for this specific area, we should go 400, here 500, here 800. What does the client want, and what are we able to achieve here?
I just have a quick.
30
Kim,
seconds.
on you're talking deep holes. Oh, sorry. Kim's talking about deep holes here. What is the temperature gradient per 100 feet? Do you know, or is it per 100 meters?
So the average temperature, if you go,
This is just interesting for the reason to go deeper.
yeah. So if you go 300 feet, so deeper, you will on average, the temperature will rise 1 degree Celsius. So someone with a calculator doing it into Fahrenheit, but that's the average temperature in the borehole will go.
Per 300 feet.
Yeah.
Per 100 meters. 100 meters, one degree.
100 meters, 1 degree on average.
Okay. Yeah.
But that's not the only benefit. You will also benefit from that you can have the bigger distance between the wells, so they will not interfere with each other. So we're not only drilling for this higher temperature, we're drilling to maximize the rock storage that we are actually working with. And it depends, are you taking cooling or are you taking heating? So what do you want to achieve? If we go deeper and we get higher temperatures, but you're actually for the cooling peak power, then it might not be a good solution.
So a brilliant man sitting over here once said, we never want to use rule of thumbs. And we're trying to design thermal energy networks and heating and cooling loads. So I'm going to go a little deeper here. We'll drill some deeper, right? Let's talk test hole data. What do you need so that we can solve this? Because we're discovering the unknown together. That's what's happening when we're drilling. And test holes are very important. So what do you see that you have right now, and what could be better?
When I see a test hole, generally what I get
The log, that is, yes.
is a TC test report from the test boring. There's a ton of information that's really good for the thermal design. And then there's about a half a page on the drilling conditions that were encountered, if I'm lucky. Maybe a page on a big project. And then I'm supposed to take a look at that and extrapolate it to 1,000 holes and put in a fixed fee bid that assumes all these risks based on that 6 lines of driller's log that was collected. Maybe verified, maybe not. Everybody's interpretation of cuttings that are coming up is a little bit different. Drilling methodology may have been identified as a needed change halfway through the drilling program in the log of the soil changes, but there's not a lot of notes that really indicate the reason for the change. There's no real detailed data collection on the things that happened during drilling. So then what am I left to do? I have to look at the date it was started and the date it was ended. Now, if it's a 600-foot hole and it took 5 days to drill, I'm gonna say this is probably a risky project. But if I don't catch that little date difference at the top, I have no idea. That is not included. And I get to figure that one out on the back end when I've got a rig that's a month behind because of all of these issues that weren't really adequately captured in the TC test report.
And to add up on top of this, and when you read the contract, it's written basically its report can be actually not really accurate, and any changes and liabilities is on you.
Correct.
The reliability of the data, the same as everything else, is very important to us. So I'm going to do 2 more questions, and I want to open it to the audience, and we started a little late. So let's talk economics of drilling. We've talked big compressors, we've talked going deep, and I can tell you the fuel burn on a 1600 CFM compressor is quite a bit, including a rig and the support. So let's talk about how do we make drilling more economical?
I mean, for us, and I suppose for you also, I mean, the drilling rig costs a lot of money, so it makes a difference if we are doing 1 or 2 or 3 wells per week. I mean, if we do 1, then we have the capex cost. For that 1 well will carry all the capex, but if you do 3 wells, then you have a third for every well. So, and unfortunately, that's nothing, we live with that. So we need to have some kind of efficiency to actually get a good cost level on geothermal. It's capex and labor intensive work.
And I agree with Kim. And it's all about basically knowing your break-even, correct? So you know how many wells you need to do per month, per week. So you know how much is your hour cost. So this is a thinking which, for example, I brought from oil and gas. Your hour cost. So you know, for example, in our current operation, we roughly estimate 1 hour is $1,000. So whatever you do, you take this number. And if you see the way to improve your operation and save one hour of your operation, does it cost you $1,000? Okay, so you break even. So you actually can save operation time, and you probably, if you push it more to operation efficiency, you can save the money as well. So you basically challenge the operation all the time. Plus, you're increasing the work hours. This is what we saw. You work instead of 8 hours, you start to increase your days. You start to work on the basically six-day work day, and you generate the teams. And then this is probably one of the key point. Work as a team. When you have a team of, for example, in our case, it's a team of 3 guys, and when these 2 guys know what will happen next, so we don't have basically. If you drill the well and your well has 6 phases, you have a phase of rig setup, you have casing, you have drilling, you have cement grouting, you have completion. Each phase, if you break down, you know what is the best time, how fast you can drill, how fast you can complete. But what the problem is, if you sum up all these phases, you'll end up, for example, with 10 hours. But the best well you deliver, you somewhere around 15 or 16 hours. The transition from phase to phase, this is where we're losing the times. And this is where the teamwork and team efficiency, when team looking for the next step and the step ahead, this is what's make a huge difference. It's not about how fast you drill, it's not about how fast you run the loops, it's how fast you transition from drilling to loops and from loops to the grouting. And then you start to take some operations offline. So your rig is running and you basically can grout offline. So this helped to adapt a lot on efficiency and to shift the job off critical path when your rig time is not connected to the sum of jobs.
How about waste creation? As we look at these drilling methods, there's a lot that's been talked about with waste creation. I come from Suez and Veolia along with drilling, and when we do something, we're a co-generator. And this is something as an industry we haven't been talking about, and it's going to become bigger. So how, as we go across the board here, you know, waste generation is a costly aspect of this techniques.
I think that the baseline character, or the baseline thing to understand as we move into a more informed perspective of waste generation is understanding when it comes to disposal what the guidelines are to be able to dispose of whatever waste we are creating. Because yes, we need these materials to be able to drill. We're going to produce these materials as a result of drilling. But understanding what those waste profiles need to look like in order to optimize the efficiency when it comes to the disposal process, decrease the cost of actual disposal, becoming more educated on what is actually involved in the disposal process outside of, I don't know, man, I just call my guy with a vac truck and he comes and takes care of it. Which is great for a one-hole project, but for a 500-hole project, that's not the answer. It's not gonna be what controls the budget. So I think it all starts with education on what is actually required to dispose of all of these waste streams that we're generating.
To be respectful to the audience, and I got a 5-minute note, though we started at 1:40. I want to open it up to the audience and be able to get some questions out there.
Just ask for you guys to share.
Questions get a free driller shirt. Oh, jump right up.
I appreciated the answer earlier about optimizing your choice of which drill technology to use based on a test bore. I'm with Dandelion Energy in the residential space where you're only going to do one in most cases. How do you answer the question of which drill to take to that site when hopefully it's the only one you're going to use? Like, what's the best sort of rule of, I know we're not using rule of thumbs, what's the best guideline around what you think you're going to find underground and which drill you would take under each circumstance of what you think you're going to find?
That's a great question, and I think one of the principal challenges for residential application, which is how do I go out there in one shot, get it done, and get it done right? But that's also what is driving the cost of a residential application higher. And what really needs to be driving community heating, because there only is one hole, there's a lot of risk that's assumed on behalf of the driller to be able to make a change in the field, be equipped and ready, and be able to absorb the time cost and added material cost to change that method to still get the borehole done without any other opportunities to go out there and do it, and no other opportunities to go and get more money. And so it really becomes an economics problem. And I think that, you know, there's still going to be local and regional experts that should be drilling on those residential locations because they're the ones that drill there the most. The larger companies that are spanning across multiple states, they probably shouldn't be going to do some one person's house in a town 300 miles away. And if they're the one that you're getting your price from, you might want to QC that against a local provider because it'll probably end up costing less, even if it costs more. And, you know, looking at a quote.
Kim, you do this all the time.
Yeah, we go over state, so we don't totally agree, but I understand fully, and you definitely need to do your homework, and you need to put time into this residential. So you need to read the geological maps, you need to read the water well logs, and of course, there is a job that we can straight away tell this is nothing that we are interested to do, and then I have them to call you, for example, and we can collaborate, and because we have different drilling technologies. So I think collaboration. I would love to collaborate with someone in Long Island because I'm actually getting quite a good amount of customers calling who wants drilling there, but we're not going there. So. And of course, there is, for residential, sometimes it's hard to tell because you're in between. Are we going to hit this or this? So, yeah.
And so, heard a lot about that test drill being critical to understanding what type of rig you want, all the way to even understanding the waste manage that you're going to be doing. So how would a general prepare to get a leveled bid when there's so many options of rigs and so many means and methods of accomplishing things? What would be the best way for a general to go out and get bids from all of you drillers so that we can be certain that what we're getting back is your best bid?
I think that this is a perfect opportunity for third-party verification and standards on test bore construction. And Brock has a lot of great ideas on this, but I really think that there needs to be a more uniform process on how test borings are completed, how they're reported, how they're bid, to make it easier on both owners and generals as well as for drillers.
I was basically going to say the same thing. Good well log, and then we're confident to bid on it.
I'll just follow up on what Robert said. I've been pushing this for a long time. Third party, sit the site with you. There's no secrets in what we do as drillers. We all have a little bit of tweaks, a little bit of differences, but the test log that comes into the beginning stages of these bids is the most crucial bit of information that exists on the project. The TC numbers, honestly, I've seen engineers ignore them to fit their borehole. But when you screw up with what that test hole data says, depending on what kind of project it is, that's a major change order, it's a major fight, it's a major dollar component that gets skipped over every single time.
That's
Not a question, but.
No, that's perfect. Do we have time for one more, or you want to wrap it? Thanks, Kevin. Kevin's doing the next talk, so.
Sorry, I just had a follow-up on the test log. So what kind of information is the most useful to have on the test log for the driller? Like, do you want to see penetration rates? And second part of the question is, if you have a campus, how many test bores do you need?
Oh, good question.
You answer it.
No, so Ball State Geothermal to multiple projects around the country and world. What is a good sample set, scientist? Is 1%? Is it 5% if you're going to do 1,800 holes? Do you have an idea? That's the big question. And if we're going to build a parking structure or we're going to do a bridge or anything, the geotechnical investigation that is done and that drill log is stamped and a third-party engineer, and it's verified as data. And that'll change our change orders from we can get to do not exceed prices on projects, and it's a big piece of having the reliability of our industry. Dmitry?
Yeah, it's actually a good question. I mean, you can basically come from science and geology, and you basically study the area, and you see if it's uniform geology, you probably can end up with one bore. But on another side, you have examples. We just recently had a project in Massachusetts, one of the National Grid projects, and it's just big parking lot. So they drilled one well on one side, and then they drill another well on another side. And one well produced 300 gallons of water a minute, and the second well produced only 25. So if you basically base your project on the first one, it's actually amazing project, so why not? But if you take into account the second well, I mean, there is many drillers actually say, God, no, I don't want to go there. So there is definitely uncertainty, and I don't know, to be honest, how to address this uncertainty. It's supposed to be some kind of contractual way, because I think the driller could not take this liability on themselves. There is supposed to be limits for this type of liability, and I think it's more contractual work. Because what I notice in this industry is kind of weird, because the constructional GC, the big companies, we're basically managing all these big projects. They put all liabilities, they just downstream it down to the driller. And then the driller, with his small amount and budget, they're supposed to be responsible for anything you can find down there, from aliens to the radioactive materials. And I don't think this is right, and this is definitely need to be addressed on the legislation level.
Yeah,
great.
That's a really good thing, guys. The greater the risk for the driller, the greater the cost, the greater the percentage he's going to put into it. The lower the risk, the more boreholes, the greater that you can bring that risk factor down in. Oh, sorry.
For recordings.
Okay. Yeah, it all comes down to risk. The greater the risk for the driller, the greater that he's going to put that margin in there. If you reduce the risk and have a large number of boreholes drilled, then you can reduce that risk to the driller, and then he can give you a very, very solid number.
Thanks, everybody. We're out of time. Grab these experts, talk to them. Thank you.
Nice job, guys.
Real quick, everybody. I'm going to steal another second off of this. The person that asked the question on how do you know which driller to choose, who asked that question? So what we found is on a bigger project, find out if the person that drilled the test bore is bidding on the job. Because if they're not bidding on the job, you got to be real cautious about that borehole.